Welcome everyone to the next Gen 4 International Forum webinar presentation. Today's presentation on the development of in-service inspection rules for sodium-cooled fast reactors using the system-based code concept will be presented by Dr. Takaya. Doing today's introduction is Dr. Patricia Pavier. Patricia is the group leader of the Radiological Materials Group Office at the Pacific Northwest National Laboratory. She's also the National Technical Director of the Molten Salt Reactor Program for Department of Energy. And she is the chair of the Gen 4 International Forum Education and Training Working Group. Patricia.
Thank you very much, Bertha, for the introduction. Good morning, good evening, everyone. It's a pleasure to have Dr. Chizuru Takaya with us. He's a principal researcher of Fast Reactor Cycle System R&D Center at the Japan Atomic Energy Agency. In 2003, he received his Doctor of Engineering degree from the University of Tokyo. His main areas of research interests are structural integrity evaluation at elevated temperatures, maintenance technologies for SFRs, optimization of design, and in-service inspection requirements on SFR through plant life cycle based on the system-based code concept. He also works on the development of codes and standards for these fields, participates in several committees of ASME as well as JSME. He serves as the chair of the subgroup on elevated temperature design in JSME, and also is the chair of ASME-JSME Joint Working Group on Reliability and Integrity Management Processes and System-Based Code in ASME. So without any delay, I thank you very much, Dr. Takaya, for volunteering and presenting this webinar, and I give you the floor. Thank you so much.
Thank you, Patricia, for introducing me. So thank you for giving me this great opportunity. And good morning and good evening, everyone. Thank you for joining this webinar. I'm Shigeru Takaya. I'd like to talk about development of ISI rules for sodium-cooled fast reactors by using the system-based code concept. This slide shows the contents of today's presentation. At first, I'd like to explain the background, and then ASME, boiler and pressure vessel code, case N-875 will be explained. This code case was developed based on the system-based code concept and provides ISI rules for sodium-cooled fast reactors. After that, current status of the development of ISI standards for SFRs, especially in JSME and ASME, and also future visions will be explained. And finally, I'd like to summarize today's presentation. So let's start with background. In the background, at first, I'd like to explain the importance of in-service inspection rules. After that, features of sodium-cooled fast reactors, SFRs, to be considered will be reviewed briefly. And then conventional standard for ISI of SFRs will be explained. There were several problems with this standard. So a new ISI rules for SFRs was developed based on the system-based code concept. And at the last of the background, I'd like to explain the essence of system-based code concept. In-service inspection rules provide requirements for periodic inspections of passive components of nuclear power plants, such as vessels, piping, valves, and so on, during the service, which is important for safety and stable operation. effective and efficient ISI is crucial to suppress operation costs, which is one of major components of power generation cost. ISI is important not only after the start of plant operation, but also even during the design stage. Actually, ISI rules affect design of nuclear power plants because the accessibility to the components where ISI is required needs to be considered appropriately in the design. Sometimes it might be more reasonable to change the design so that ISI can be exempt. Like this, ISI is important from various points of view. So ISI rules need to be developed rationally by considering relevant features of reactor type and design of an individual nuclear power plant. So as you may already know, but sodium-cooled fast reactors have several different features from the conventional light water reactors. This table shows a comparison of operating conditions and the dimensions of reactor vessel as an example of the main components between PWR type LWR and SFR. More precisely, MOJ prototype fast reactor in Japan. Of course, sodium is used as coolant material in SFR. Sodium is opaque and chemically active, which makes it difficult to apply the traditional or conventional ISI technique to SFRs. Needless to say, visual tests using camera cannot be used under sodium, and conventional ultrasonic and surface examination not as easily performed as in LWRs because of the limitation of the accessibility. On the other hand, sodium shows excellent compatibility with structural materials. In SFR, the corrosion is negligible in purity control sodium, while the corrosion such as stress corrosion cracking is one of the main concerns in SFR, in LWR. Reactor outlet temperature is above 500 degrees C. It's in creep regime, so creep and creep fatigue interaction damage should be paid attention for as a typical degradation mechanisms for SFR. High thermal stress and low pressure, and these features of dimensions are also related to failure modes to be considered in SFR. Like this, there are significant differences between LWR and SFR. So it is not reasonable to apply the ISI rules of conventional light water reactors to SFRs directly. Historically, the American Society of Mechanical Engineers ASME Boiler and Pressure Vessel Code, Section 11, Division 3, had provided ISI rules for liquid metal cooled plants, as shown here. Section 11, Division 3 was developed as part of the Clinch River Breeder Reactor Plant project in the US. Clinch River Breeder Reactor was sodium-cooled fast reactor, so it is considered that this Division 3 is for sodium-cooled fast reactor. However, the code revision was suspended due to the cancellation of the project. The several parts, including acceptance standards for examinations of Class 1 components, were left as being in a course of preparation. So it was practically difficult to apply to SFR plants. To address this situation, ASME-JSME Joint Task Group for System-Based Code was established about 10 years ago in the ASME Boiler and Pressure Vessel Code Committee. As a result of collaboration between experts from ASME and JSME, code case N-875 that provides alternative ISI requirements for liquid metal cooled plants to Section 11 Division 3 was developed based on the system-based code concept and was issued in 2017. A fitness for service code for sodium-cooled fast reactor was concurrently being developed in JSME, and the first edition was approved last year. So before explaining the details of code case N-875, I'd like to explain the essence of a system-based code concept. By the way, the code of the system-based code concept doesn't mean the kind of simulation code, but kind of codes and standards, the set of provisions. The system code-based code concept was originally proposed by Professor Sada about 20 years ago. There are various technical areas related to the structural integrity of components, such as load, material design inspection, and so on. And margins is given in individual technical areas kind of independently, and then accumulated like this. But how much is not clear, maybe too excessive. On the other hand, in the system-based code concept, target reliability for the total integrity, the structural integrity of the component is determined first, and then the component is designed to meet the required reliability. The margins are distributed to each technical areas. How to distribute the margin is flexible as long as the total integrity meets the reliability. So margin exchange between different technical areas are also possible. And such margin exchange makes it easier to expand technical options. If owner or users want to employ the technical option with less margin, they only have to add additional margin in the other technical area to meet the target reliability. Such a flexible and consistent concept of the system-based code is very useful to develop the ISI rules suitable to the SFRs by considering the features of the SFRs. From now on, I'd like to explain the ASME boiler and pressure vessel code case N-875. At first, overview of the code case N-875 will be presented, and what ISI is required alternatively to Section 11 Division 3 will be explained. And then logic flow to evaluate the applicability and the key technical elements for the evaluation according to the logic flow will be explained. And the last part of this part, example will be presented. So as already mentioned, this code case was approved in about 5 years ago. This code case provides alternative ISI requirement to Section 11 Division 3 using the system-based code concept. The code case composed of the main body provides alternative provisions of the logic flow to establish criterion for the application and 2 mandatory appendices. Appendix 1 is a derivation of component target reliability from plant safety requirements. Appendix 2 is procedure for structural reliability evaluation for passive components of liquid metal reactors. Several key parts of the code case have been incorporated in the new Section 11, Division 2, requirements for LIM program for nuclear power plants, as explained later. This table shows a comparison of ISI requirements between Section 11, Division 3 and Code Case N-875. Code Case N-875 covers these 5 examination categories: liquid metal retaining wells in Class 1 vessels protected or not protected by guard vessels, liquid metal retaining wells in Class 1 piping protected or not protected by guard pipe or tank, and internal components. As for liquid metal retaining wells in Class 1 vessel or piping, continuous monitoring and VTM2, a kind of a visual test, are required by Section 11, Division 3, while just only continuous monitoring is required by Code Case N-875 if the conditions are identified by using the SBC concept is satisfied. And the acceptance standards for the continuous monitoring was in the course of preparation in Section 11, Division 3, but in the Code Case N-875, the acceptance standards for continuous monitoring were newly prepared. As for internal components, VTM3, another kind of visual test is required by the Section 11, Division 3, while Code Case N-875 requires no ISI for internal components if the conditions, especially conditions, is satisfied. The acceptance, go back. Acceptance standards for continuous monitoring in the code case was prepared by using the related provisions in the Division 3 and the experience in Japan. Once leakage is indicated, it is required to conduct a confirmation of leakage in accordance with the procedure predetermined by the owner. If the confirmation takes longer time than the determined type, it is conservatively evaluated that the leakage is confirmed. In the case that the leakage is confirmed, immediate shutdown of the system is required. And in case that leakage is unconfirmed, it is considered the indication was due to fault of the monitoring system. So a repair of the leak detectors is required to meet the minimum percentage of required working leak detectors. So this is a logic flow to establish criteria for application of the alternative ISI requirements, as explained in previously, maybe 2 slides before, based on the SBC concept. The logic flow consists of 2 evaluations compensate each other. Stage 1 evaluation is structural reliability evaluation, and stage 2 is safety-related evaluation. Both probabilistic and deterministic approaches are applicable. And this logic flow is originally developed for this code case, but it could be for a general use. Actually, it has been incorporated in the appendix for alternate requirements for NDE and monitoring in the new Section 11, Division 2. So I'd like to explain stage 1 and stage 2 evaluations in a little more detail. Stage 1 is in the stage 1 evaluation, the component level structure reliability and the design basis conditions is considered. Potential failure modes are determined based on the degradation mechanism identified based on the inputs from this load resistance, environment, and configuration. And the component level requirements, CLRs, are determined in deterministic or probabilistic manner based on the input-related safety evaluation. Component level requirements established in a probabilistic manner is called target reliability in this code case. And then the reliability of the component is evaluated. At this moment, the contribution of ISI is not taken into account. Evaluated reliability and target are compared, and if the evaluated reliability meets the target, the CLR, the user may proceed to the stage 2 evaluation. In the stage 2 evaluation, the ability to detect flaws and that ensures the plant can be safely shut down before the flow reaches the maximum acceptable size is considered. Either direct or indirect detection is allowable, which is make it possible to select suitable ISI technology flexibly according to the plant features. In the case postulate flaws are not detectable, no and no, we proceed to the reliability evaluation with a penalty. This additional margin is demonstrated by imposing the penalty in a structure reliability evaluation. Examination for flaw detection is not required, which is a margin exchange between different technical areas via the penalty. So from now on, I'd like to explain key technical elements needed for the evaluation according to the flow, logic flow. The first one is determination of failure modes. The degradation mechanisms that can potentially produce flaws during service is evaluated based on the list of the potential degradation mechanisms provided in the code case, as shown here, as well as operating and research experience. Failure modes are determined based on the identified degradation mechanisms. And failure modes not addressed in the design code are also considered if necessary. Next is determination of CLRs. Component level requirements. CLRs are established either deterministically or probabilistically based on the input related to safety evaluation. Deterministically established CLRs are quantities such as the break size postulated in an accident scenario that define the allowable limits from the safety point of view. And probabilistically established CLRs are component level target reliabilities derived from quantitative plant level requirements available in quantities such as core damage frequency, containment failure frequencies, or large early release frequencies. A method for derivation of a component level target reliability is provided by the Appendix 1 of the code case. In the Appendix 1, to derive component level target reliability, a probabilistic risk assessment, PRA, is used. A PRA is usually used to integrate the individual reliabilities into the risk index In that case, a structural reliability is one of input for PRA analysis, and risk indices such as CDF, CFF is output. On the other hand, the developed method used PRA in a reverse way to derive component level structural reliability from plant level risk target. In this case, target structural reliability is output, while risk target is one of the inputs. Target structural reliability is determined to meet the risk target by using PRA analysis models under provided conditions. To compare with target, reliability needs to be calculated, but calculated structural reliability could vary depending on which and how uncertainties are considered. To narrow such scatters of calculation, Appendix 2 uniquely provides the procedures for structural reliability evaluation for passive components. The procedures consist of the failure scenario setting, modeling, and failure probability calculation. JSME developed guidelines on reliability of fast reactor components, as shown here, and the appendix in the code case was developed based on the guidelines. The next is evaluation of detectability of flaws. As explained, the basis of stage 2 evaluation is detectability of postulated flaws. Not only conventional direct detection, such as ultrasonic examination, but also indirect detection is allowable. And two new indices for indirect detection were introduced in the code case. The one is maximum acceptable leak, MAL, which is applied for coolant boundary items. MAL is a leak that would not lead to an increase in the CDF or CFF RAF that has been calculated in the safety evaluation of the plant. The other is intentional discontinuity, UID, which is applied for non-coolant boundary items. UID is a change in the plant parameters, such as temperature and velocity of coolant, that indicates that flow exists before they lead to an increase in the CDF, CFF, or RAF that has been calculated in the safety evaluation of the plant. By expand technical options, a suitable ISI method could be selected according to the plant features. The last one is reliability evaluation with penalty. If postulated flaws are not detectable, reliability evaluation with a penalty may be conducted. If the result meets the target reliability, the examination is exempt. To show that the component has enough margin even without ISI, unrealistically conservative yet logically imaginable penalty, which is correlated to the highest consequence failure mode, is determined from the following 4 categories. The first one is load. Additional load caused by failure of an adjacent component or part of the component that reduce the loads on the critical portion of the component. Second one is resistance. A decrease in the resistance caused by loss of strength, enhancement mechanisms, or metallurgical stability. The third one is the environment. A presumption that the component is subject to the most harmful environment postulated as a component location. And the last one is configuration and initial flaws, such as anticipated flaws or distortions. So far, I explained the logic flow and related key technical elements. From now on, I'd like to show some examples. according to the logic flow. Evaluation of according to the logic flow. Actually, several trial evaluations have been conducted for the components of the prototype SFR in Japan module to illustrate the developed logic flow. Upper core structure, core support structure, reactor guard vessel, and class 1 piping. Today, I'd like to show the result of a core support structure and class 1 piping as an example of the probabilistic approach case and deterministic approach case, respectively. The first one is the core support structure. Probabilistic approach was employed in this case. This table shows the basic information on the core support structure of the module. The function is to maintain core configuration, and the CSS was made of the type 304 stainless steel and used in sodium. Maximum temperature is about 400 degrees C. It's high, but under the creep regime. The main load is cyclic load by reactor startups and shutdowns. CSS is categorized as internal components, and Section 11, Division 3 requires VTM3, which is visual examination, intending to determine the general mechanical and structural conditions of components and their supports, and to detect discontinuities and imperfections is required. While code case N-875 requires no ISI if the condition is satisfied. It is mentioned in the Section 11, Division 3, visual, for example, periscope and light, or combination of the under-sodium scanning and dimensional gauging is available. But of course, conventional visual technique using periscope and light cannot be applied if the vessel is filled with sodium. So, firstly, failure mode has to be determined. Potential failure modes have to be analyzed exhaustively, even if they are not addressed explicitly in the design code. First of all, corrosion in the purity control sodium is negligible, and the temperature is low enough to neglect creep damage. On the other hand, material properties might change due to the neutron irradiation. For example, decrease in ductility is one of concerns, but the surveillance program during the operation is available to confirm the neutron irradiation effects. The looseness of the fixing bolts may be another concern, but preventive measures against the rotation of bolts were taken in the module. So, as a result, just fatigue damage due to cyclic loads by reactor startup and shutdown is left. Next is establishment of the CLR. Probabilistic approach was employed for CSS. Current level requirements are needed, but those values are not available for module. However, such a discussion was made for demonstrations SFR in Japan, JSFR. So those numbers are used in this example. That is, CDF is less than 10 to minus 6, CFF is less than 10 to minus 7. And then plant level requirements is distributed by considering the plant PRA scope, whether initiating event is internal events or external events, whether initial plant operating state is during plant operation or shutdown state, and so on. These distribution factors are determined by the owner consistently with a plant safety design concept. As for the our example, the initiating events is internal events. Initial plant operation stage is power operation, and failure of CSS directly results in core damage. So the failure of CSS due to fatigue damage are categorized here. By using these numbers and also considering design life of the module is 30 years, as a result, less than 6 times 10 to minus 6 was obtained as a target for failure of CSS due to fatigue. So in this, in the stage 1 evaluation, crack initiation evaluation was conducted. Crack initiation was assumed when fatigue damage df equals to 1. N is number of cycles and NF is fatigue life. Evaluation position is at the mount arm from the RV, as shown here. Precisely speaking, this part is not part of the CSS, but except for this position, there are multiple load transfer passes to maintain the core structure. So this part was selected as the evaluation position in this example. And direct Monte Carlo method was employed for calculation method. Number of samples is 10 to 9. And summer stress and fatigue life was chosen as random variables. The result is shown here. A horizontal axis is fatigue damage df, and here is a criterion for the crack initiation. And the vertical axis is 1 minus cumulative probability. As shown here, the number of crack initiation samples was 0 out of 10 to 9. So it was shown that the components CSS has sufficient reliability. So we proceed to a stage 2 evaluation. In the stage 2 evaluation, detectability of flaws is evaluated at first. However, the appendix for the under sodium scanning in section 11 division 3 was in the course of preparation. So it was assumed that the under sodium scanning system were not available yet in this evaluation. And it was also assumed that there were no monitoring method to direct flows in CSS. So we proceed to reliability evaluation with a penalty. In reliability evaluation with penalty, as penalty, a fully circumferential crack with depth of 10% of the thickness that is too large to be missed was assumed as an initial defect. And crack growth evaluation was conducted. And 50% of pore thickness was selected simply as failure criterion. And the direct Monte Carlo simulation was conducted. Number of samples is 10 to 9, and summer stress and the coefficient in this equation was selected as random variables. The results are shown here. Horizontal axis crack depth, and vertical axis is 1 minus cumulative probability. Initial depth is here, and failure criterion here. As you can see, the crack hardly propagated, and the number of failure sample was 0 out of 10 to 9. So it is shown that component has sufficient reliability even with penalty. So based on this evaluation, it was concluded that alternative requirements of the code case N-875 is applicable to CSS module. That means no NDT is required. So next one is a second example. Second example is primary heat transfer system piping. The function is primary heat transfer, and this piping was also made of R-type 304 stainless steel. Inside of the piping is sodium, and outside is inert gas. Maximum temperature is above 500 degrees C. It's in creep regime, and the main load is cyclic load by reactor startups and shutdowns. This piping is categorized as a liquid metal retaining class 1 piping, protected or not protected by guard pipe or tank, depending on the position. Section 11, Division 3 requires continuous monitoring and VTM2, which is a visual examination intending to detect accumulations of liquids, liquid streams, liquid drops, and smoke. On the other hand, code case N-875 requires only continuous monitoring if the SBC condition is satisfied. So based on the similar discussion as a previous example, a crack initiation and propagation due to fatigue creep interaction damage was selected as a failure mode for PHTS piping. And next, the deterministic CLR was established. The break size postulated in the plant safety evaluation can be used as a deterministic CLR. As for the PHTS of module, a wall-through crack with opening area of 22 square centimeter was postulated in the plant safety evaluation. So this wall-through crack with opening area of 22 square centimeter was selected as a deterministic CLR for PHTS piping. So in the previous example, the probability of crack initiation was evaluated, but as a matter of fact, fatigue as well as fatigue creep interaction damage is already addressed by the design code. And therefore, fatigue creep interaction damage of PHTS piping is restricted below the design allowable level. So it is considered that the crack would not initiate and propagate to the sites determined as a CLR in the condition of the PHTS. So such a deterministic approach was applied. We can proceed to stage 2 evaluation. In the stage 2 evaluation, detectability of flows is evaluated. In the module, 2 sodium leak detection system is installed for small scale leaks. One is sodium ionization detector (SID), which detects a leak by monitoring a change of ion current produced by ionizing sodium aerosol in an inert gas atmosphere. The other one is differential pressure detector (DPD) that detects a leak by monitoring a change of difference pressure as a filter installed in the detector. These detectors are designed to detect leaks of 100 grams per hour. And next, MAL, maximum acceptable leak, should be determined. In the plant safety evaluation module, a slow wall crack with an opening area of 22 square centimeter, this was selected as a CFR, was postulated, and the leakage rate just after the accident was evaluated to be approximately 80 kilograms per second. So as you can see, the capability of leak detection of SID and DPD is much greater than the MAL, the determined MAL. And in addition to the capability of leak detectors, demonstration of leak before break is essential to show the effectiveness of the continuous monitoring. Leak before break is a concept that is leakage is detectable before break, so plant can be shut down safely. So, and in this example, guidelines for LBB assessment of SFR provided by JSME was used. This is procedures provided in guidelines. Unstable fracture assessment, leak rate assessment, and penetrate crack assessment was conducted. And if critical crack length CR is larger, both detectable crack length CD and penetrate crack length CP, it is considered LBB is demonstrated. As for this example also, LBB is successfully demonstrated. So postulated faults are detectable. It was shown that postulated faults are detectable indirectly. And based on this discussion evaluation, it was concluded that alternate requirements of code case N-875 is applicable. That means just continuous monitoring is required for the PHATS piping. So here I'd like to explain current status of development of ISI standards for SFRs in JSME and ASME very briefly. In JSME, standards related to ISI of SFRs are developed based on the SPC concept. As already mentioned, fitness for service code for sodium cooled fast reactors was approved last year. General rules and ISI requirements of class 1 components and their supports are provided in the first edition. And of course, continuous monitoring is required to coolant boundaries as code case N-875. At the same time, guidelines for LBB assessment of sodium cooled fast reactors are developed and approved. The guidelines are available to determine the required sensitivity of leakage detectors for continuous monitoring. The guidelines for reliability evaluation of sodium cooled fast reactor components are also developed. This is unique guidelines providing procedures of reliability evaluation, which is important for the system-based code concept. And in ASME, a brand new fitness for service code for all types of nuclear power plants, Section 11, Division 2, Reliability and Integrity Management was published in 2019. Section 11, Division 2 provides technology neutral requirements and supplements for specific type of nuclear reactors, currently for light water reactor and high temperature gas reactor. This is a flowchart of the LIM, but as you can see, the LIMs share the basic concept with system-based code concept. And actually, some part of the code cases has been already incorporated in the Division 2. The procedures of deriving the target reliability in the code case is incorporated as mandatory appendix 2 in the Division 2, and logic flow and reliability evaluation procedures are included in the non-mandatory appendix A. As I said, currently supplements for the sodium cooled fast reactor was not included in the Division 2, but development of supplement for liquid metal sodium cooled fast reactor cooled reactors is one of the top priority action items of Section 11 committees. Therefore, ASME, JSME Joint Working Group on Lean Processes and SBC is now developing the supplement based on the ASME Section 11 Division 3 code case N-875, and GSME standards, including LBB assessment guidelines for SFRs. So lastly, I'd like to talk about future vision. This figure is an image of the structure or hierarchy of the standards. Top of that is safety goals, and the safety standards are prepared to achieve the safety goals. And structure standards are prepared to support safety standards. However, the relationship between structural standards and the safety standards sometimes unclear. Sometimes it is difficult to say what safety functions is implemented by following certain provisions in structural standards. So closer link between safety standards and structural standards is essential to develop nuclear power plants that balance safety and economic efficiency at higher level. A reliability target or target reliability is a promising key concept to link both standards. And also, technology inclusively development of standards is important. Is essential to develop standards for various types of advanced reactors efficiently in a timely manner. The structure of LIM, the combination of common part, technology neutral part, and specific part, a specific rules for each reactor part is very reasonable. And such structure is important from the view of the explainability. If the common part are shared among all type of reactors, the adequacies of that part, the common part, cannot be explained repeatedly. And as explained in this presentation, the flexible and consistent concept of the SPC is expected to work as a basic principle to develop technology inclusive standards, and also a specific rules for each reactors. A summary: effective and efficient ISI is crucial for safety, stable operation, and economic efficiency of nuclear power plants. SFRs have several desirable features such as excellent compatibility between sodium and structural materials, while traditional volumetric and surface tests are not as easily performed as in light water reactors. The system-based concept can be used to develop ISI rules rationally by considering relevant features of reactor type and design of individual nuclear power plant. ASME, boiler and pressure vessel code case N-875 is a good and important example of development of codes and standards based on the SPC concept, and the details are introduced in this presentation. Recently, the new Section 11 Division 2 LIM has been developed for various advanced nuclear reactors. LIM shares key concept with SPC, and the case has been partially incorporated in the LIM. GSME has also developed a new fitness for service code and related guidelines based on the SPC concept, and link between safety standards and structural standards, as well as development of the technology inclusive standards are important for advanced reactors. SPC concept is expected to work as a basic principle. This is end of my presentation. Thank you for your attention, and I'm happy to answer questions. Thank you.
Thank you. Thank you, Dr. Takaya. As questions are coming in, we'll take a quick look at the upcoming webinar presentations. In October, a presentation on the sodium integral effect test loop for safety simulation and assessment, abbreviated as STELLA. Again, you have the registration link and the information flyer describing that webinar in the handouts pane today. In November, a presentation on the visualization tool for comparing energy options. And in December, the mechanisms engineering test loop facility at the Argonne National Laboratory. So we do have some questions that have come in. Dr. Takaya, I have elevated you so that in the questions pane, you can undock that. And sometimes it's easier to see the questions as I read them aloud. The first one is, can this methodology or code be used to other liquid metal cooled reactors like liquid lead or LBE?
Thank you for the question. So as I mentioned, the strategy or the logic flow is can be is applicable to other type of reactor, not only liquid metal or other type of reactor. Actually, the the logic flow was included in section 11 division 2, which is not limited the target reactor. But of course, the specific methods such as crack growth evaluation or something like that not directly applied. But so the essence or the key part of the methodology can be used.
Great, thank you. The next question, do you expect that the owners or designers will build an additional margins? For example, perhaps a bolt backing out of the core plate is not a safety issue, but it could be very expensive or time consuming to repair. And a related question is, do you anticipate that the regulator will want to review the additional margin elements as some part of the defense in depth?
Thank you. Do you expect the owners or design will build in the additional margins? Afterward, okay. Do you, as the regulator, want to review the additional margin element as some part of defense in depth? Yes, it's a good question and important questions. Yes, in this code cases, it's focus on the safety issues, but in the same manner, the such kind of in the same manner, the such kind of issue can be considered. For example, the stable operation, not safety issue, but some time-consuming manner or something like that. So, but I think what is important is what is requirement from safety issues and what is the requirement from the other objectives. So how to determine the target is related to these issues, and the logic flow or the methodology to derive the target reliability is kind of answer to that question. And regulation, do you the regulator want to reduce additional margin elements as some part of defense? Defense in depth is also important. Important point, but so for as I said, the logic flow consists of two two parts: stage 1 evaluation and stage 2 evaluation. So even if stage 1 clears, that means evaluated reliability means the target reliability. It is required to proceed to stage 2 evaluation from the safety-related point of view. So, in such manner, the defense in depth is also considered in the developing the this logic flow.
Thank you. What is the definition of class 1 components?
Class 1 components is the reactor coolant boundary.
Thank you.
Such as,
If you have additional questions, go ahead and type those in. And while we're waiting, I'll wait just another minute. Again, thank you, Dr. Takaya, for your time and sharing your expertise. It's been a pleasure to get to know you during this webinar presentation. And we look forward to hearing more from your efforts in the future.
thank you very much.
I don't see any additional questions coming in. There is a link for the email. If you have something that comes to mind later and want to reach out directly, you can do that. So since there are no further questions, I think we'll go ahead and end it for today. Patricia, did you have any closing thoughts?
Yeah, no, I would like to just say thank you to Dr. Takaya again for volunteering to give this webinar, and I would like to thank the audience to participate in all these webinars. We need you again. As Berta said earlier today, you have the possibility of a survey to give us some thoughts about how we're doing, and also suggestions of webinar that you would like to hear about or understand a little bit better about the subject. So thank you very much, everyone. Thank you again, Berta. And thank you, Dr. Takaya. Wish you a very good day, very good night. Bye-bye, everyone.
Bye-bye.
Bye-bye, thank you.